And so we're going to be recording this for those who are not able to attend. And again, thank you for coming to the seminar. And so I'm going to take about 45 minutes for this presentation, and then I will switch the presentation off and open the chat room to get any questions and try to answer your questions as best I can. But let me just give you my contact information in case you're not able to ask any questions, or if you'd like to, if you think of any questions afterwards. And so this title slide gives you a couple of different ways of either emailing or calling or texting me. And so what I'd like to do is give this presentation and give you some of the reasons why I put together this presentation. But before I get into the purpose and the reasons why this is an important topic in terms of what we're experiencing around the world, I'd first like to start with an acknowledgement of people that and places that have influenced my thinking about diagnostics and about public health and the work that I do in public health. So first, I got involved about 10 years ago, going to a seminar at the University of Washington School of Public Health. And it was very interesting, a week-long seminar where they brought people from the sciences and engineers and anyone who was interested in public health who really didn't have any background in public health. And so I thought that was a really fascinating topic, and it got me interested in what kinds of things I could do with my engineering background. Another acknowledgement is for Dr. Vidal de la Cruz, who I've known for a long time, a childhood friend, and we continue to collaborate to this day. And he is a person I've collaborated with a lot about the ideas that I'll be presenting towards the end of the presentation. Dr. Carlos Machain Williams, who's another professor in Mérida and the Universidad Autónoma del Yucatán in Mexico. And he's an expert in virology in animals. And then I'm going to be talking about some modeling work that people do around the world in terms of creating computer models. And the GleamViz team is a team that's been around for a number of years. And we'll talk about the models that they make available and how you can even download these things on your computer to understand some of how people are talking about propagation of diseases, especially in our current situation with COVID-19. And the Netlogo community is a worldwide community for people interested in a different kind of mathematical modeling. And we'll be talking about one of the models that Paul Smaldino has made available for anybody to download and to use. And then the data we'll be looking at is from the Johns Hopkins Coronavirus Resource Center. And then also Valerie Harris, who's a doctoral candidate in biological design, and she's currently involved in getting CLIA approval at Arizona State University, and she's the one who introduced me into using Netlogo for the purposes we'll be discussing in this seminar. So this talk is not meant to be a talk about the medical aspects or the biological aspects. So I just want to make sure that you get information on that, and hopefully this talk will be a series of talks around campus and where experts will also share some of that information. I'll be limited in terms of just talking about mathematical models of how we understand how infectious diseases can go through the world. And then also look at some of the ways that we can use our knowledge about infectious diseases and knowledge about how technology can be used to mitigate some of these effects. And hopefully spark some creative thinking, some curiosity on your part to learn more about how do people go about making decisions, how do people go about using data, and what are all of the experts talking about currently, and what they will be discussing in the next few weeks as the world grapples with this pandemic. So the first thing, I guess, is to also mention that we live in an information-rich world where we can get a lot of information at a fingertip. This is something that came up on LinkedIn, and I thought I'd share with you. So there's lots of information in different levels of scientific detail. And so right now, currently, we hear about the coronavirus testing. For those of you who want to learn more about this, there are more experts on campus and more places to go for this kind of information. But basically, I put this here just to remind us of a couple of things that are important to note. One is that I will be talking about positive cases, and so that data is based on these kinds of tests, specifically these genetic tests to test for the presence of the RNA of the virus in people that are suspected of having the COVID-19 disease. And that these tests have, they're not 100%, but they're the best tests we have available. And so they're used to interpret any kind of suspected cases. And so the data that I'll be showing you and the information in the models are based on results from these kinds of tests. So certainly some of you may have already seen this kind of information. This is a poster by Andy Brunning Compound Interest 2020. There's a recent post on LinkedIn. So I won't go into the details of this again because I think that's for another kind of talk, but we should be reminded as to the fact that these tests are the basis for the data. So there'll be three things I'll focus on in the talk in some depth before I talk about some ideas about what we're doing now in mitigation and what kinds of things we can do in the near term that we're hoping to really make this change in terms of the course of the pandemic, and then what are the things that we might be able to see in the future and some things that people might think about for the longer term future of us dealing with infectious diseases in general. The first model is much more of a mathematics, and so mathematical kind of model with equations and graphs and lots of data. So that's called a continuous curve in this talk, and I'll go through that in some depth because we'll be comparing. I'll be comparing the data from the Johns Hopkins Coronavirus Center with this kind of modeling approach. The next one is briefly talk about Netlogo kinds of models. This is a very different approach. It's called an agent-based model. It's basically a game that you run with rules that are done through writing in this Netlogo language, and then you can run the simulation. You run this game, and it provides data as well as visual cues, and that helps to provide insights into mechanisms, especially relating to these kinds of diseases and how they propagate within the populations. And then the third one is a little bit more visual. It shows some of the more classic public health kinds of modeling that people do in different laboratories and research areas, as well as statistician models that you might have heard of in the news. And these are called stochastic framework models. And they're based on what we understand in terms of how do we group different populations in the course of an infectious disease. And so I'm going to focus on one way of looking at this, and that's called the SEIR model. And through this modeling, you can also develop a little video, and I'll show that video with a particular made-up kind of case, rather than talking about the COVID-19 pandemic. And I think that's going to be of interest to people. And again, all three of these are easily accessible to anyone who wants to use any of these models or has a computer, and you can generate models of these three types. So the first one is what I guess an engineering approach is what the title of this talk is, because I think it's important for me to explain that as engineers, a lot of times we use mathematics in a different way than what would a scientist or a mathematician use mathematics. A lot of the mathematics we use is for design, but also mathematics and mathematical models are used in engineering in order to better understand a process or a situation or a kind of an idea that you want to use in terms of creating a new design. And so this is a very much simple type of equation, and this is known as the Verhulst model. it's over 100 years old in terms of being described as something that you would use to explain a dynamic situation, as we call it. In other words, something that occurs over time. And in this case, we're going to be using the Verhulst model in terms of generating a prediction on the total number of positive cases of a disease like COVID or any other kind of infectious diseases in a population. And so the equation that this is represented by the dots here of cases versus time is given here, where n is the number of positive cases, and with respect to time, k is the maximum reached in that population. So k would represent the total number of people who could possibly get infected. R is the rate at which the infection moves, or the speed at which the infection propagates. And C is another constant that relates to the initial part of the infectious disease process, or the pandemic, in our case, process. This is something we'll talk about when we look at the data in more detail. But these three values, or these three symbols, K, R, and C, are what we would be called the parameters of this model. And then some of you may be more familiar now in the news with this same idea, the same equation, shown in a slightly different way. And here it would be the derivative of the Verhulst model. And this shows the rate of change, or the change in the population of positives over time. And the parameters are the same here in terms of K and R. And what you see here is a peak in the number of cases over a period of time. And then this is at the early time of an infectious disease propagation. And then this is the later times. And so some people are now referring to this more popularly as the curve that we are looking to flatten. And so the data, this is probably the most recent that I had, and this every few hours, I think this is updated. The data I'll be talking about comes from the Johns Hopkins Coronavirus Resource Center, and this is available on the web. They've been tracking all the data that they've received, and they provide this resource. Some of you may already have seen this, and it lists by country, it lists the total in the world, and it gives a graph, and here in yellow dots on the bottom right-hand corner, of confirmed cases. And so what I'll be focusing on really is the data from the confirmed cases, all these yellow data points over the time that the database has been available and is available for anyone to view on the internet. And so without going into all the details about how to do this mathematically, what you can do with the Verhulst model, as I showed you before, is that you have three parameters, K, R, and C, that you have to, in terms of trying to use that equation as a prediction, you take whatever data you have available, you make what we call a fit to the data by adjusting those three parameters. Typical engineering approach to understanding understanding the system using a mathematical model. And then from that, you go ahead and make predictions. And so what this slide shows is a pretty complicated slide, so I'm going to go through it relatively slowly. But the good news to remember here is that the prediction that I made on March 25th, I did this on purpose. I decided before this presentation that I would take data up to a certain time, make a prediction, and then see at the day of this presentation, which is April 8th, how good or bad my prediction was based on this model and based on the data, and then report back how things are going. And so in this case, I'm happy to report that even though these are stark numbers, the predictions were way off. If we looked at the data early on in the pandemic and tried to project out how many people would get the disease, would be much higher than what is looking to be the trend globally at this point in April 8th. And so in this case, like I said, it's good to be wrong, in my opinion. And so rather than potentially having worldwide 10 to 14 million positive cases, even though there's 4 million is a lot of people, obviously a lot of suffering in the world. But the idea here is that, in my opinion and the opinion of many other experts, I think many of the measures have been taken so far, and in terms of all the public health measures, have been making a huge difference in making these kinds of predictions a few weeks ago look like they were way off, way overestimating. The other thing that's really important is that this is an S-shaped curve, as I showed you before, is what the model is based on. And so the orange data are all of the, the orange data are all of the COVID cases before March 26th. So it's all the data up to March 25th. And then the yellow data points are the ones after March 25th. And so it's harder to see here, but you could tell that the trend is a little bit lower in terms of the speed at which the total number of cases is moving up with respect to time. And so here, this is expanded because now the equation that you fit all of the data we have available and as close as possible to this Verhulst model prediction, which is the blue line, we see that this is a much better fit of the data. We obviously have more data, but the other thing about it is that the estimates now have to be much lower in order to assume that everything is going to follow this trend and be predicted as we can tell from our current state of measuring positive cases over time. The other thing that is noticed here is that a few weeks ago, it looked like the pandemic, in terms of the total number of new cases, rapidly increasing every day, would be another 2 to 3 months of that period. And based on this model, again, which is just a mathematical model, this looks like the length of time may be around 2 months, and depending on how you want to call flattening of the curve or the slowing down the number of new cases. It gets a little tricky here, and because this is an S-shaped curve, so it's a very complicated kind of curve, and as you get closer and closer to where it flats out, it's harder and harder to see the differences in the number of new cases per time. And so that's why the derivative, or this kind of a mountain kind of curve, is shown here. And it's a little easier to see that according to this model, according to the data, and according to what we're seeing, we're getting closer and closer to this peak time globally, where we are expecting to hit worldwide the maximum number of cases. And so, and then this idea of interventions can change everything. It seems like it is changing lots of things in terms of the prediction from March 25th to April 8th. And again, some people have been talking about this. Some statisticians have been making the same point, that it is tough to make predictions, especially about the future, which is a quote attributed to Yogi Berra. Now, this model, as I showed you before, that last bit of a peak that I showed you, would be relating to this kind of a curve. And here is something you've probably seen in the news, where the number of cases is plotted versus time again, and they trying to illustrate the fact that if we don't control the rate of transmission, in this particular case, this disease propagates very rapidly through a population, and it could show a peak that's very high, and it reaches a maximum at a very short period of time. By flattening the curve, which is proactive measures, we would get this kind of change to be much lower, and so the peak is lower, but also the amount of time that it takes to reach that peak is much longer, and that helps in terms of being able to have the right capacity at the right time around the world. And so again, just to remind you of the last bit of data that I showed, and the last curve that I showed of the Verhulst model, the derivative there is is very similar to this kind of way of plotting the data. But that model is very limited because it doesn't say a lot about how diseases propagate, and it doesn't predict much in terms of what can you do other than looking at the slowing down the rate and slowing down the number of people that might get exposed, or minimizing the amount of people around the world that could be exposed to the virus. And so the next model that I wanted to briefly explain is a model that is based on more complicated programming, and it's not based on a simple equation. And this is a model from the program Netlogo, which is available for free for downloading. And this particular model is of COVID-19, trying to explain how this virus propagates, but in a very different way, without using necessarily the data exactly, but using the ideas behind how we understand the disease propagates, and how what is the purpose of the interventions, what is the purpose of social distancing, isolation, and trying to do all the measures that you've heard about in the news. This model is by Paul Smaldino, and I show you two screenshots that I downloaded the model, downloaded Netlogo, and ran the model for two cases where there's a parameter here, I hope you can see that is called the speed bar, and the speed here is written as a value of 3. And so and the way this works in the model is that you create a universe, which is these little, this black screen with white, it looks like little cartoon figures of people, and then some of them are in red. And the idea behind this is that you can run a series of rules and some computer code and give it some parameters. And so with this model, you can look at the difference between an uncontrolled, let's say, a propagation speed of the disease of a value of 3. And this is a relative value done by the program, just to illustrate this point of flattening the curve. And so the curve that we're looking at and the output of the model over time is a simulation where this moves around quickly, gives you a certain period of time, and they call these things ticks in this program. And the ticks can represent days or whatever time period you'd want it to represent. And the curve that we're most interested in is this curve called infected, which is the red curve. So if you take all of this model with all of the parameters, except for the fact that you lower the speed of transmission from 3 to 1, and what you see is that the screen here doesn't look much different from this screen in terms of the number of red people and the number of white people, because it's just a cartoon figure of red being infected and the little figures of people in white being non-infected. But the result is that because the simulation tries to explain how infections propagate and how visually we can tell by how many times does a red person in this simulation game comes in close contact with a figure that's in white, and that turns that figure in white red, you get this peak. And so in this case, the peak is not as high as this peak. So again, the flattening of the curve idea, a little wider than this one, and the peak of the infected goes from a value of 0.764 to 0.567. And so that's what this model is teaching, is what happens if you keep everything the same, but you decrease the speed of the interaction. And that speed of the interaction would be kind of a surrogate or a way of understanding how we can slow down the rate of transmission. And so that's what Paul Smaldino's, he has a website where you can download this model, and he explains this in more details since he teaches in public health. So this is a great kind of model because it's simple and it's very powerful. So the idea behind Netlogo is that kids can learn how to program in it. The agents are called turtles, so the people in that simulation are called turtles. And so it's, rather than writing an equation, or rather than having a very complicated diagrams, this business of speed and how speed can be used as a surrogate to explain the transmission of a disease is done in this code by just saying move the turtles and move them randomly in 360 degrees, get a new random heading, and then move them forward with whatever that speed is. And so these kinds of simulations in Netlogo are a series of very simple commands, very simple rules, but you let it all play out. And it's deceiving how powerful Netlogo is. It can be used in a very complex way for very complex simulations in supercomputers, or it could be used by kids playing interactive games. And so it has a wide utility, especially in understanding complex dynamic processes such as propagation of disease. So again, that's two models. One model was a continuous curve model. It seems to can be followed by the data. It doesn't have a lot of mechanistic information. Here in Netlogo models, which are agent-based models, you create these rules. You can create some mechanisms. You can talk about speed. You can talk about number of people infected, and you can get different results. But so those are two types of models. And the third model I wanted to show you is one where you can now start looking like the type of models which most people do in public health when they look at epidemics. And so that's where the program GleanViz comes in. GleanViz, again, is a group of people from around the world that have generated easily accessible information built into this model. You can download GleanViz onto your computer. You can learn how to use it. It's very easy to understand, but very powerful because you can add a lot of information about the world, about what the infectious mechanism is like, and what kinds of parameters or what kinds of values based on epidemiology you can then ascribe to in this model. So there's a link here to GleanViz, pretty easy to remember, gleanviz.org. You can just type that in Google and click it, and you can get much more information about GleanViz. So what I did here, just to illustrate the power of GleanViz, is I downloaded the SEIR, I downloaded GleanViz and created an SEIR model, which is a set of differential equations, and they're shown graphically here. So each box represents an equation, and these equations are based on how we understand the rate at which a susceptible person is then exposed, and how an exposed person becomes infectious, and how an infectious person then can become recovered in this process. And so rather than show you the equations, GleanViz gives you these boxes, and it gives you boxes that you can then choose different things. You can add information about travel. So are susceptible people traveling around the world? Are they traveling by car and plane? And if you have an exposed case, is that a person that you now need to track, or if you want to, you can look at limiting the travel or not limiting the travel. And then in an infectious case, this is where it's very important to limit travel. The simulations that I'll show you don't have this restriction. So you can do a simulation where you can allow this to happen, and then you can also restrict the travel of a person that's that may be infectious by some measurement or some testing, and see how the simulations work out, and see if there's any difference in the results that I'll show you in about a minute or two. And then the same in the recovered. And so these beta, epsilon, and mu's are parameters that you can set. And the idea behind those is these are fractional parameters. And each disease, the experts will look at clinical and public health data and estimate these parameters and run these kinds of models, along with models about how our world works in terms of how people interact and how people move around, and what kinds of population centers, relatively speaking, the different population centers, what kind of travel there is, as well as trying to understand over the course of a year how a disease might propagate around the world. And so, for example, this is a screenshot of showing the information you can get from GleanViz. It gives you a map of the world. It will give you the peaks that I showed you before, and it gives you both of the curves that I showed you before. And if you remember the Verhulst model, you have this S-shaped curve, and then here is the flattening of the curve where we're looking at the number of new cases over time. This is the number of cumulative cases over time. So here I have a simulation which I thought would be illustrative, just to get you thinking about how these models work and what kinds of things we need to consider. So in this case, we're going to pick a model where 100 people in Albuquerque are infected with a new disease and has never been seen in the rest of the world. And this simulation is based on lots of data already existing on how people travel around US as well as travel all the way around the world, and how the people around the world travel. And so it gives you an idea as to how fast or how slow a disease would propagate depending on where it starts and how many people are initially infected. So in GleamViz, if those of you who download it or want to learn more information, it will take at least 30, 40 different parameters that you need to feed into the model in order to then start the simulation. So if I can run this simulation, I won't run it in real time. I'm just going to go through it really quickly. This simulates in the matter of days what would happen. And so, as you would think, early on in an infectious disease that starts in the American Southwest, such as Albuquerque, you would think that that the number of cases are popping up in dark colors. They're going to be more limited to places in the U.S. as well as other places in the North and South America. And then as we move along, we start seeing quickly a jump in cases in parts of the world where we know that there's a lot of travel, which is Europe as well as Southeast and Asia, Southeast Asia and Asia. And as we move along, you start seeing the number of dots increasing in density, and you notice that in the early stages of the disease, you will see that some parts of the world are going to have more of these cases and more of these cases in red. And then as we move further, what you'll notice in the simulation is that high population centers around the world, like places like India, Southeast Asia again, and places closer with high population near the origination of the disease are going to be also highly red. But what's interesting is to see what happens in terms of this kind of modeling, this SEIR model, which is a common kind of model for people to understand infectious diseases, is that as we go further, it takes longer, but you see continent of Africa getting a number of cases. Again, these are based on lots of assumptions about how the disease propagates and how people move around the world, and how long it takes to go from infectious to recovered. All of these things are built into the model parameters. But towards the end of the infection stage, which is simulated here by a full year, we start seeing parts of the world now no longer have these cases. People are recovered or removed in terms of the simulation. But there's some lingering numbers scattered around the world. And that is the entire idea. So again, if I go back and forth with this, you start understanding the way that the waves will come in our current pandemic, and how things originated and then became hotspots in different parts of the world, and how waves of these hotspots are then propagated depending on the travel that happened before any interventions were taken, as well as people realizing that they need to stop traveling to other parts of the world and to curtail the amount of spreading. So again, this is available. GleamViz is available by download, and you can create your own simulations and also use data that's available in public health to run through a number of different scenarios. So now that we've talked about some of these models, I think I'm going to try to relate in the last few minutes of the talk as to what technologies do we have. The technology we have that seems to have made already an enormous effect in terms of reducing the speed of transmission through the human population is what I show here. The social distancing is showing great utility and effect. when the public responds. We're already seeing that the projections of a few weeks ago are already are being dampened quite a bit. And that's the hope as we continue on the next few weeks, is that this effect will continue and it'll be even stronger, which is as well as limiting travel early on. Different parts of the world limited travel in different stages. This isn't shown in the simulation, but it can be done in the GleanViz model, as I mentioned, in terms of how you run the simulation. But certainly this is also another way to reduce the speed of transmission through the human population. And then all of the measures that people are doing in terms of personal protection and cleaning surfaces. So this can be modeled again through more easily through a Netlogo kind of model and even a GleanViz model. But Netlogo allows you to do that more graphically. You can write rules and look at ways of looking at how this could reduce the speed of transmission. Changing environmental conditions are another important area of reducing transmissibility. And so that's why people consider that the effects of the transmission of this disease will be noticed as the weather changes around the Northern Hemisphere. And then testing and isolating positive. GleanViz certainly, if we look at that model and redo it so that we have a clinical case and those people are isolated, as well as a Netlogo model, those can be written to simulate those effects as well. So reducing the transmission through technologies that are being worked on as we speak, I think that's the second level of what you hear in the news today, and I think is the one that makes the most promise in terms of many different developments that we're hearing each week. And the first one is vaccines. Vaccines are a tried and true method of instantly converting the kinds of results that we're seeing and making lots of people go from being the regular population that's susceptible and no longer being susceptible, so that they will never be able to have the full disease. And so another thing about vaccinations is that the herd immunity can take place even if you don't vaccinate everyone. And so this is known to be around 70% for most infectious diseases. So as a tool for public health, certainly a communicable disease where you can generate a vaccine, get it to at least 70% of the population, can completely turn around any kind of infection, course of infection. And certainly there are lots of promising research that suggests that this particular SARS-CoV-2 virus is susceptible to vaccination based on our understanding of the two previous coronavirus transmissions. And so there's a lot of promise in this. This is a slower technique. It's going to take continued animal testing, human trials, and so that process may take a few more months. And so in the meantime, the treatment cure is right now being tested, as you probably have heard. This treatment cure in clinical trials, it's important that we understand what the benefits can be of different treatments and cures. There's a wide range of treatments and cures being pursued, especially treatments involving isolating antiviral compounds and/or using people that have recovered their antibodies as a way of helping someone who's in the later stages of difficulty with the disease be able to recover without having to go through the whole process of a disease course. So these are important tools, and it's something that we're seeing a lot of promising results. It's going to be a number of weeks still until we understand how that will work in terms of the general population, because right now it's in clinical trials, and also it could be a very important step towards a vaccination, which may take about a year is what some people are projecting to take for the vaccine. And then full testing and isolation. This is a very challenging task, but I think we've already seen people be very successful with this, different parts of the world where they are doing as full testing as possible and then isolating those people that test positive. And so every week it seems like there's more testing coming on board. And so this is the opportunity to do this. And by doing this isolation, as well as doing more expanded testing of different kinds, I think everyone points to that as being one of the more important mitigations that's going to occur. So for me, in terms of a person interested in engineering and interested in designing new ideas, and also interested in trying to get lots of other people interested in biomedical devices and designs, here's some ideas that I'd like to close with. And these are obviously just ideas that are, some of them are general, most of them are all of these are in the research stage, but they're based on different observations and different data that's available and scientific theories that have been available in the research literature. So one idea to share with you is that we know that in this disease, there are some people that are very vulnerable to some of the more difficult courses of the disease, especially pneumonia. So can we test people ahead of time to determine the most vulnerable population, and then using that information really mitigate the kinds of vulnerabilities, especially the load in terms of the human toil, as well as anything on the medical system, any kind of burden on the medical system. So I'll talk a little bit about this idea. Some people have learned some things from the previous coronavirus infections due to SARS, CoV, and MERS. And so some are noticing that this is a possibility as well for the SARS-CoV-2 virus. More far-fetched, I guess, or more research needed is that we're doing pretty well in terms of understanding how to clean surfaces, especially how to design antibacterial surfaces and how to clean surfaces and areas for both viruses and bacteria. But what's tantalizing is, can we change our built environment, is where we have buildings, where we live and work, and where we travel, and can we design surfaces that are antiviral? Can we use some knowledge and to try to figure out how to keep viruses from being very active, or keep surfaces clear of them? And so we know that in this particular case, it's a problem, because as you probably have heard, the COVID-19 disease and the SARS-CoV-2 virus seems to be able to be still viable on surfaces over days. And some of the research is still controversial as to how long it can be active on surfaces. But this idea, I'll give you a couple of pieces of information about this. But again, this is a little bit further down the road. And then one of the goals that I know that a lot of people have been working on, but still is further out in terms of our abilities to do this, is can we detect emerging infectious diseases? And this has been a topic that keeps coming up in public health technology, is can we have biosensors, and can we monitor our environments and look in the future for potential threats? And that is something that I'm not going to really talk about, but it's something that you can Google and search, and there are many interesting ideas around this. And certainly this idea of having living biosensors, or having ways of looking at different potentially emerging diseases quickly, is going to be a continuous topic in the area of public health technology. So the first one is, it's a little bit more developed in terms of research idea, is can we narrow the focus to vulnerable populations? And so I've been working with a group to look at what kinds of things can we do with rapid testing at home, or without having to use a hospital or a clinic. And so the idea behind this in terms of COVID-19 is, can we figure out more about how to use a rapid test, a test strip format, which is being looked at a lot for a number of reasons for testing. But here the testing idea is more about not necessarily testing for the particular disease, but testing whether some people may be more susceptible for the virus to get into the tissue, into the cells. So one piece of research in previous SARS epidemics has been that there's a particular cell receptor that is important for the COVID virus, as well as the SARS-CoV-2 virus to actually get into the human cell, and that is called the ACE2 receptor. And so this idea is, can we design a saliva or urine test that can be done at home very rapidly, and can it detect the level of this receptor so that people who have a high level of this receptor may need to have either treatments to lower the number of or block these receptors, as well as make sure that these individuals are monitored and are also given some special attention in terms of social distancing or isolation. So this is based on some research that I've been involved in. And certainly this idea of the ACE2 receptor monitoring could be used in a hospital setting. So our idea is that if we can do some rapid testing and it can be done at home, we'd be able to test a lot of people. And if it's a small fraction of people that have this high presence of ACE2 receptors, then you narrow down the type of people that you would focus on, and hopefully, again, be able to mitigate some of the most alarming symptoms, as well as the worst course of this infectious disease. So in order to get this technology moving, we have the idea. We're looking to get partnerships for people to work with us, and that's what I'm currently involved in, and getting the resource to extend this current technology, as well as understanding how this could possibly be used specifically for COVID-19 pandemic that we're currently exhibiting. The second idea that I wanted to share again is again more of a futuristic idea, but can we design antiviral surfaces? It's important that we now have tools to clean surfaces well. That's undergoing, but can we make a surface that we don't have to spray, or we don't have to go through extraordinary measures, but it can stay anti-active in terms of viruses? And so one idea stems from what we know about is a lot of bacteria, as well as certain viruses, do not withstand high exposures to ultraviolet light, especially UVC light, because ultraviolet light can disrupt the genetic material. And so once that genetic material is disrupted, then you would prohibit the reproduction of the gene of the virus. And so this is a cartoon taken from one of the vendors of selling these UVC types of lights. And so this struck me as an interesting concept, is that while UV light is not something we want to expose ourselves to all the time, is that still possible? Is it possible to do that? And so what I suggest here is that, can we create a UV saturated surface by taking some technologies that have been developed for upconverting nanoparticles? And so in this case, UV saturated light is a possibility if we can take a surface and put a coating of some materials that will actually take ordinary light and emit ultraviolet light. And can we then keep the surface kind of bathed right near the surface, so that this area would be something that would constantly be disrupting the protein or the genetic material of any virus that might hit the surface. So this is a completely new idea. It hasn't been tested, it hasn't been proven, but it's just a way of thinking out loud as to how do we go about even trying to design an antiviral surface. And so again, a challenge to anyone who wants to be creative and think more thoroughly about this, I think this is going to be a very important area in the future. We have, like I said, antibacterial surfaces. We have some materials to clean surfaces of viruses. We don't have materials per se that are specifically designed to be antiviral. So concluding remarks, I have two quick concluding remarks, is that unfortunately, a lot of people are predicting that this is not the only time we're going to be seeing propagation of SARS-CoV-2, that there's a possibility that we can get another wave of this disease and come the fall, and you might have heard about that in the news. And the basis of this is based on what we understand of about 100 years ago, the so-called Spanish flu. So this is, again, a graph that I found on social media, and this explains how what we call the Spanish flu actually started in Kansas, and it was it then went through a dormant period where there were some people infected, but we didn't notice that the infection was still propagating in the population. And then with World War I, it was propagated worldwide and became known as the Spanish flu. But what's not very much discussed in history books is that even after this wave occurred, another year later, there was a wave of infections that was documented in the course of this propagation of this disease worldwide one more time. And then finally, concluding remarks looking to the future, we definitely are taking advantage of the CDC and World Health Organization recommendations. As I showed you before, people are making a difference around the world in terms of mitigating what people thought would be predictions in terms of the propagation of the disease worldwide. And there's also some interesting things about how we should be doing this even better. There's a neurosurgeon that has a video about how you should wash your hands, and this is on YouTube. Certainly, we're learning too that telemedicine is important. So people are using telemedicine more and more now to talk to doctors if you have a suspected symptoms. This, I think, is going to be a time where we're going to see an expansion and continuation of telemedicine. And then another area that's really important, which is what is happening now on all over the internet, is people who are not necessarily medical experts are coming up with new ways of looking at better public health mitigations. How do we provide personal protective equipment? How do we sterilize it? Everyone is getting involved. The public is involved in donating supplies. Students are coming together, NMSU, to develop different things that we can donate to in terms of 3D printed masks or shields, as well as being able to compound alcohol and to make hand sanitizers, and potentially make other things that will help first responders as well as people deal with mitigating the propagation of the disease. Certainly global cooperation is needed. Technology to share more information on health is another area that we're finding to be an important thing to do in the future. And then obviously we're now realizing that medical research on infectious diseases is going to be an important thing for all of us to be involved in. And so at this point, I wanted to break out of this and go into the chat room and see if I can read some questions in the remaining time that we have. We have about 6 minutes. So I'll see if I can read some of the questions. So one question here, is anyone else looking at environmental control systems, like sort of like HVAC in buildings? And so that's a good question. So the idea there is, can you create a way to improve the environment within of the air in the building? And I think that there are some examples of how to do that in terms of air handlers that either have high filtration capacity filters that can filter the air very cleanly, as well as use UV lights to try to inactivate any bacteria or anything else that's in the particles. So if there are any other questions, you can use the chat box. So just one comment here. I guess some of you can see this. I took control of the chat room so that I can manage all of the information here. So there's another comment here that's pretty fascinating. There's an antimicrobial zinc and copper oxide nanoparticles into textiles. So this is another example of, you know, how would the antimicrobial zinc and copper and oxide nanoparticles, and I think even silver is used in certain kinds of materials, what would that do to viruses? And that's a good question. So being able to answer that question would require some testing, and I think the originally intent in these materials were to keep them mostly decontaminated or keep them clear of mostly bacteria. So that may be another area. So I don't know the answer to that in terms of how it would work with the virus, but certainly something to look for. And then gamma rays and killing the virus is another question. I'm not an expert at all in what kinds of radiations can deactivate viruses. I would assume that energy of any kind can cause a lot of protein damage to the surface of the virus, and so I would also say that's something that should be looked at in terms of being able to decontaminate an area quickly, because sometimes it's easier to use these kinds of systems to decontaminate. How much radiation and the intensity, that would be the area of research. And then models that include, another question about models that include seasonal factors like the 3 Spanish flu waves. And that's an interesting question. I looked at the GleamViz and to see if there was a way of incorporating that into the structure of GleamViz. And I'm not sure if it can be done. And it might be doable. I think that it's some of the parameters in the model, if I remember right, take that into account. But if it's not obvious, there are several layers of GleamViz that need to be explored. But if it doesn't have that, I would be surprised. And certainly the GleamViz team are very accessible. You can email them and ask them if they've taken that into account. I do know that the models that people use, the statistician models, the public health models, are very sophisticated. And they're much more expansive than what I just demonstrated. So I think they definitely take into account the transmissibility, the survivability of the active virus based on these changes, as well as the movement of people based on these changes. Okay, so why is the design of a face mask so controversial? I think the face mask controversy, I guess, is based on a couple of aspects of a face mask, which is how well do people wear them? How tight is the fit? And how well it can stop someone from inhaling what could be a particle that may contain an active virus. And so those are the hardest things to understand, because we're taught in biotechnology biosafety. And so there are three levels of biosafety. Biosafety level 1, or BSL1, which is the least restrictive. BSL2, where you need some restriction and you need to have special equipment. But in BSL3, which is what we would categorize handling or being near someone that is infected by this particular virus, because it doesn't have a treatment for it, that would normally require your own respiration system, so that you're not even in communication with the air around where the virus exists. And so these masks don't go to that level. So how protective are they, these N95 masks? They seem to be fairly protective, but there is a chance that if they're not used correctly, if they don't fit well, or if they have a defect, you can easily communicate with the outside air, and you might be able to expose yourself. If you use a regular mask, you're not going to have the filtration capacity, and you're not going to have the close fit that these much more complex masks are designed to have. So another good question, which is why should we wait for the summer if there's a seasonal variation? Why not look at the data of populous countries in the Southern Hemisphere? So makes sense that those things need to be looked at. But as it turns out, there's always the travel element as well. So the transmissibility can go down, but then if people come from other places, and so is that going to affect that isolated population and how they might be in a different seasonal zone in the Southern Hemisphere, and whether they have either more transmission or less transmission? That becomes part of the dynamic that I think is complicated. The other thing could be that seasonal variations may be based on large population centers. And so some of the larger population centers around the world seem to be in the Northern Hemisphere. A lot of them seem to be in the Northern Hemisphere. So the next question is logo modeling for smaller units of analysis, county, city levels. And I think, yes, I think the Netlogo modeling could be used for different situations. You create different rules, you make different assumptions, and you could even add little pieces of code that will accidentally bring a new person in. And so you can simulate the kinds of things you would see locally. And I'm sure that people work in this environment, this agent-based modeling environment, to do just that. So, right, thank you. And so, yes, the virus is very small, nanoscopic, but the droplets can be microscopic. So that's important. How the virus is carried and the environment that it needs to be carried on, which is mostly a droplet of some kind, that's what we take into account in terms of the effectiveness of the filters that are needed in the mask. So I think that is the most important part of how to do that. But you definitely need a good fitting mask, and you definitely need to be able to assure yourself in the quality of the mask that there isn't a way for these tiny droplets to be able to get through. So this is an area that I think a lot of development and a lot of technology is going into right now, is what kind of personal protections we should be recommending. How do we do it? How do we integrate it within society? How do we certainly do it for first responders and the medical system, especially when we're relying on these things for people that are coming in contact with populations that are infected with the virus. So with that, if there are no other questions, again, I'm recording this, and so welcome you all to provide more questions or contact me. And also, if you get a chance to download this recording, and we'll be putting up on the cloud and give you links so that you can access it and get more information and go through these models on your own. So it's been a pleasure, and be safe and continue to heed all the recommendations by our public health officials. And again, thanks a lot for joining me.